welcome guys. So this is a very short video about how to use a variational principle to derive the Schrodinger equation. So derive SE. Okay, so we know that SE in 3 dimensions, right? Looks like this. Right, so this is the simple quantum mechanics, like the time dependent problem, right? So the next, but the things that we want to construct a Lagrangian, right? So Lagrangian, and then we start from the how we use the variation principle to get something like this. Okay, so and we need to treat phi and phi star as a different variable. So key is that you write down some terms or contains function contains this psi and psi conjugate, and hopefully you do the variational problem that you get the answer. You get the Schrodinger equation. Okay, so the key is that how to construct this L. How to construct this L. Okay, so let's quickly start. So I think the reason is that there is a So we start from there's a normalization property that you assume that the usual wave function should satisfy it. So it's right. You conjugate psi the one, right? And we know that our Hamiltonian looks like this. So we are trying to work out backward, right? So let's say if we put psi star and h, right, and put on psi dx. Let's focus on the x. Sorry, this is dv, right? Let's focus on the x directions. So we only focus on x directions. Then this term, the kinetic term, is basically this. And then you can do the integration by part. Then you will get this one. Okay, so just do a stupid integration by part. Right? You integrate with this, and then you see if we assume that this turns 0, then somehow like we get something very strange, right? We get something like partial phi star, partial phi, partial x, right? So it looks like this is in a 3-dimensional, right? It looks like all of these terms can be viewed as a gradient, right? So that means ideally we can write a Hamiltonian into like the form like delta of this. So we just change this one, right, into this one, dot with this one. Okay, so just like this term, right? So we can change it into this, and then we put star by star, and the dv is 0. Okay, so actually this is the Schrodinger equation if you derive it, right, by our definition. Since we already, once we assume this term is correct, then we can change our original Schrodinger equation into Lagrangian form like this. Okay. Okay. And that's called G. Okay, so let's call G to be this. Okay, and the theorem is that if you do the variation on G, then you will get the answer. Okay, so the proof is that you know that there is a constraint, right? So so when you do the Lagrangian, you need to add G equals divided by lambda, right? Minus lambda by some constant. Then let's call G tilde, right? And then you do the partial G tilde divided by partial like phi star. Then you see when you do a phi star, right? Then let's say you will get okay, so let's maybe do it slowly. So your Lagrangian equation looks like this, right? So this star partial x, partial g, partial phi star x, right? So this is phi x, partial y, partial g, partial phi y star, minus partial z, partial g, partial phi z star equals to 0, right? So let's say what is this partial g partial psi star, right? So partial g partial psi star, you get the v psi, right? So you get the v psi minus lambda psi. So lambda psi is here, right? Derive g tilde, sorry. Okay, and the derivative on this term, right? You get the partial x, right? So you get the partial x h squared divided by 2m partial x. So if you combine 3 terms, there's another, right? And another. Okay. Then you will get a v sine minus lambda sine minus h squared divided by 2m and the partial x. So this is combine of this Lagrangian phi psi here. Okay. So you will get 0. So this is okay. So this is the Schrodinger equation. Okay. So finally we get an answer. Okay. So actually this is the this one is a Lagrangian density for the Schrodinger equation. And if we treat psi star and psi independently, then the Euler-Lagrange equation gives us the correct representation of the Schrodinger equation, at least for the time independent. Okay, and I will see you guys in next videos, and hope to subscribe to my channel. Thanks.